Sounds good. Welcome. This is When Connections Are Magic, and I'm James Burns. But it turns out that this is really when connections are not magic. So currently, I do research at Lightstep. Previously, I'd done SRE-like roles at Stitch Fix and Twilio. And in those roles, I'd seen a lot of interesting different behaviors of public APIs. I'd been close to various engineering teams within cloud providers trying to work through those issues. But the thing was that I basically couldn't talk about that ever due to NDAs. And so I thought that this might be an interesting opportunity as part of my research to do some public SRE, to be able to talk about and demonstrate best practices for understanding performance, or looking at how behavior changes over time. And so I decided, if I'm going to do that, why not throw in a few buzzwords like observability or cloud functions or APIs. And so I built out a cloud function in Google Cloud Functions written in Go, and it was meant to simulate the transformation of some data for just-in-time responses to web browsers from a cloud storage. And I was going to do Google Cloud Storage, and I thought, well, I might as well do Amazon S3. It's about the same. It'll make an interesting comparison. And so I had some assumptions about what was going to happen. I thought that, you know, S3 going cross-cloud would maybe be 30% slower based on some other cross-cloud work I'd done. But I got this together, I rolled it out, and I got data. And the data did not look quite that cool. In fact, it looked pretty odd. And so it looked a little bit like this. So these are the histograms for the performance of on the top, a request to GCS, and on the bottom, a request to S3. And you can see there that they're more than 2x difference, not the 30% I was expecting. And so I started thinking about this. I started working on a mental model about what may be different from my expectations. And I started trying to figure out, how can I see what's really happening and why? And so because it was lower than my idea of what would happen, and I suspected that probably had to do with networking, I wanted to focus on that. But the thing was, because I'd chosen to go serverless, which was actually really handy and very fast, I couldn't actually just jump on the instance and start looking at packet dumps. I couldn't just dive in and see the performance. And so I started looking around about how other people had addressed this issue, and I found a package called HTTP Trace that was available for Go. And what it does is it gives you callbacks that come with some certain information about different phases of a connection. And so just a quick review of what those are. At the beginning and end of DNS, it'll give you these callbacks with information about the DNS process, including what lookup was done and what the results were. As part of the connection process, TCP, it will give you information about what it tried to connect to, and then what it actually did connect to at the end of that. During the TCP process, TCP negotiation, it will give you a callback when it starts, and then it'll also give you information about the TLS connection that was eventually negotiated. And lastly, it gives you a callback when it's finished writing the HTTP request, and then when it gets the first response back. And so there's some assumptions built into this that I didn't fully realize actually until I was putting together this presentation. The request writing is dependent on the size of the request, so that is usually very slow, or very short. And then the first response byte, in my case, I wasn't transferring very much data, so it was essentially the same size as the completed response. But if you were transferring a lot of data, this wouldn't be the most accurate place to look at the full amount of time from the first byte to the last byte. So I had these different callbacks that were available to me in serverless. But the thing was that tying them into traces, there still wasn't an out-of-box solution. So I had some additional constraints in this case. So I wanted to instrument code that I didn't directly control. And so that was the SDKs from Google and AWS. And so I started looking about how people solve this problem. There are a few different solutions that involved like changing every line of code that made an HTTP request, and that was obviously a non-starter. And so I just started basically looking for other code that used HTTP trace, and I came across the Xray SDK, which is Amazon's performance checking and distributed tracing tool. And I looked at how it was implemented, and it looked pretty slick. It looked pretty good. It was all open source. So I took a look at it. I took a look at the license and said, hey, I can change this to do what I need. And so in the course of actually only an afternoon, I was able to take it from using the Xray API to use the Open Tracing API, which is what we use at Lightstep to collect telemetry information from distributed traces. And so I had that, but then I still had to figure out a way to get the clients, the right way of integrating HTTP clients inside of the Cloud SDKs. And it ended up looking a little bit like this. So it actually ended up looking exactly like this. There are different methods depending on what kind of authentication ends up being built into the client. And that's why there are three different things. So using no authentication, it's just a simple HTransport, which is Google's API client that generates an HTTP client. When I was using environment credentials, I put those in with a jot config from JSON there and got out a config that allowed me to then get an HTTP client. And in the last case, it's just the default case for Google that gives you an HTTP client that uses the regular priority of authentication sources. And then with that HTTP client, using this, I called the library Xray port instead of Xray, I wrapped that client into a trace client. And what that meant was that for each one of these callbacks that got called, it would take the information and create a span, which is a measure of the amount of time it takes to do something. And then those spans become related to each other by parents and children, so that you can see a distributed trace, which is a collection of spans that starts in a certain place and tells you how much time an operation took, and then each one of the little pieces underneath that. And so at the end of that, I got this trace. And surprisingly, this actually made sense as to what was going on with performance. So to understand why, let's walk through the numbers. So overall, there's the attempt in this case is the label for the fetching of the file. And then so the phases inside of that are connect, which is all the things that need to happen before the HTTP request can be made, and then the request and the response. So if we look at the amount of time that's taken here, for the first one, sorry, having some slide issues here. So for the first one, it takes about 76 milliseconds, and so that's one set. Okay, sorry. Yes. So what underlies that and what makes that make sense is the phases of the connection that this goes through. So the first, all this text is love text. The first part of this is the TCP connection. So SYN, SYNAC, ACK is usually something that some people have heard sometime. It's the handshake that opens the TCP connection. And then the next set of communications are the TLS negotiation, and there's a whole bunch of other messages that are left out, but basically client hello, server hello, client key exchange, and change cipher spec. And then once you have a TLS connection, then you make an HTTP request over there. And I've added in this difference between the API and the storage, which we'll see why that ends up being the case. But the important part is these round trips. So TCP is 1 round trip, TLS is 2 round trips, and HTTP is 1 round trip. So now going back to this trace, we can see what that means and what that implies about our network performance here. So first, there's the TCP connection, which is 1 round trip, which shows as 76 milliseconds. And then the TLS negotiation, which is 2 round trips, which is just about 2 times the 1 round trip. And then last we have 101 milliseconds for the response. And that is about 75 milliseconds plus about 25 milliseconds to actually do the work of getting the data and returning it to the client. And so we can see how knowing how the network works tells us that these numbers make sense and they explain the performance. So let's look at what the odd data was. In the first case, there is the GCS Cross Region. So if you're in one region, say Asia East 2, and you're accessing things in Europe West 2, what I was seeing was the implied network latency for TCP and TLS was really small, and then the implied latency for the HTTP request was really long. And I thought about this a while, and I realized that the way that Google has their API architecture is that they terminate the API connections close to the client, and then they use their RPC network behind that to actually do the storage fetch. So looking at that, it made sense that it was only the fetch to storage in the other region that took a long time. And then I was looking at AWS, and I saw this. I saw all long round trips basically, and the same kind of look at like what's the API architecture for AWS, and it's highly regional. So that if you want to make a request to another region, every single packet needs to make the full round trip to that region. And you go, well, that still isn't that far, right? But if you have a globe still, or if you can get a globe, I actually did this in VR. There's this insight, like if you end up thinking about the world as being flat because you spend so much time looking at maps and seeing a relatively small world. But if you trace your finger across that distance, in this case from Virginia to London, it's a long way. And so it starts to make sense that even at the speed of light, that this takes a long time to make those round trips, and that produces a significant performance difference. But that wasn't the only thing I saw. The almost main difference I saw was connection reuse. So instead of any kind of connection setup, there was just the request and response. And what I saw was basically reuse almost every time from the Google Cloud Function to GCS. And this confused me because no matter how long I waited, the first connection would be reused. So I expected that in the Cloud Function, when I invoked it, it would start up the process, and it would additional connections might be reusing the same one, but the first connection should be in a process that was initialized in response, and that was not the case. So I wrote up a research report. I submitted CFPs and said, connections are magic. Google Cloud Functions injects stuff in the runtime and makes things super fast for Google. Posted that. People said this is really interesting, great. Nobody actually reproduced the results because I open sourced it hoping that someone would reproduce the results and tell me why they were not magic. After I got an acceptance to do a talk on it, the next day I got it running in Lambda, because that was the main complaint, is that it was not apples to apples. It was so I wanted to do an apples to apples comparison in Lambda, and I got it running in Lambda, and I saw connection reuse, because connections are not magic. And it looked like this. So there are some odd things here still, but the main point was Lambda making requests to GCS had connection reuse on the first connection, for quite some time. So if it's not magic, if it's not the runtime doing something inside the function, then what might be? And I started going through the different dimensions that I'd expected performance to vary on. I'd expect it to vary by the provider, by the region that was being the source region and destination region. I'd expect it to vary by the service and cloud. And I wondered what I was missing. And basically, after thinking about it for a while, I thought maybe it's connection frequency. And so I was able to see both cases of connection reuse and not connection reuse in Lambda, but I couldn't tell what was making the difference. So for GCS, I started trying to make requests less and less frequently. And sometimes if the Lambda was cold started, yes, I would not see reuse. But if I was making connections even up to every night, once every minute and a half, I was still seeing reuse. And that was basically when I lost the patience to keep waiting a few minutes before every request and decided to address it the other way. And so I started looking at S3 and I figured out how fast can I make it. And so I started at 1 second and I saw lots of reuse, not every single connection, but about 80% of connections reuse the existing connection. And so then I started backing off the request rate. And when I got to 7 seconds, I saw no reuse. And so because the initial case was once every 60 seconds, and 7 seconds is less than that, and 90 seconds is more, then the results made sense. It wasn't magic. But why does the GCS SDK maintain connections so much longer? I still don't know, actually, and that goes to further research as needed. So some of the things, some of the odd things that I saw that I haven't directly addressed yet. First, TLS latency. So when I first set this up in Lambda, I just used the defaults. And the default for a Lambda function is to use 128 megabytes of RAM, which I thought that's no problem. This is a super simple application. It's small. It only does one thing. That's not a problem. And then so I started seeing this odd behavior where the network latency on here 1.13 milliseconds for TCP, and then the HTTP is 27.5 milliseconds, which is basically all the RPC call. And then you have TLS here taking almost a second. And I thought about it and I thought, well, that sort of looks like throttling, but like I don't understand how that would happen. And so I looked around for people to talk about different issues that were similar, and figured out that it probably was CPU throttling. So the amount of memory for Lambda correlates with the amount of CPU allocation. And so I ended up bumping it up to 256 megabytes, and these essentially went away. So that's interesting and something to watch out for if you're doing network connections in Lambda. Next one I saw was GCS OAuth. So the default method for GCS to get the credentials it uses for an API is to use a certificate bundle to reach out to an OAuth endpoint, which then gives it back a token that has a shorter lifetime that then it uses to go make the request from the API. And what I saw was that was taking a significant amount of time. In this case, almost 50 milliseconds. And because of the way that process is architected inside the SDK, I couldn't, or at least I couldn't figure out how to get access to that piece of the HTTP client that would have wrapped that. And then next was this odd thing. So here we have a connection. The amount of time taken in the connection phase is clearly the majority is DNS at almost 78 milliseconds. So you know, that's a long time, but who knows? The thing is, if you look at the rest of it, this is in AWS from Lambda to S3, and you can see the implied network latency is well, it's small. It's like 10 milliseconds at most. And you see DNS here at 78 milliseconds, and you wonder how AWS Lambda looking up AWS 3 is taking that long. I still don't have an answer to what's going on there, but without this being visible, I just think, oh, it's sort of slow. And with this, I can say, hey, DNS is slow sometimes. Maybe that's something I need to look into. Another thing, multimodal fetches. So I ended up using, because of that OAuth delay that was irregular, I ended up changing the authentication to use the S3 emulation available in GCS. So it would just use HMAC signing of the request, which doesn't require a round trip to an API for authentication. And so using that, because it was a significant performance improvement, I still saw this. So in some cases, this is a histogram. It shows in log the amount of time it took to do something and the count of things that took that amount of time to do it. And you see here 2 humps, meaning that there's 2 different distributions of the amount of time it takes to do this fetch. And so normally you'd go, well, what makes those 2 things happen? And you'd look for differences, and you'd expect it to be connection reuse or some kind of regional difference. There was no difference on any of the dimensions I was able to observe between those 2. So that also is pretty odd. And this is pretty new. So this just started happening about a month ago. What we see here is a time series view of requests, and this is, I believe, between US East 1 and Europe West 2. And normally those take 273 milliseconds, which makes sense as a total round trip time given the things that are in play in terms of the network. What we have seen start to happen is that it starts taking 1.72 milliseconds, which isn't even enough time for a local connection normally. And so what this implies is that the API gateway itself is directly providing the response from some cache, probably. But this gets turned on and off randomly. It's actually right now mostly on. This is from some time ago now. But this is something that Google just turned on. All of a sudden, all your requests would be faster, and you wouldn't know why. And then they would be, 100 times slower or 200 times slower, and you wouldn't know why unless you're able to observe this. So that's sort of the context and the process I went through to understand the performance of these cloud functions and how they varied across different qualities. But I'd like to step back and talk a little bit about what was part of my thought process and the system for this. And when you want to observe a system, when you want to observe the behavior of something, you need to figure out what matters first. Because it's really easy to add lots of metrics, lots of traces, whatever else, and still not get the information you need to understand the system. Usually there's a latency component to it. So how long does it take for the thing to respond? But it's important to understand how the variance matters. Do you care about that only from one region, one location? Do you care about it globally? How do those expectations differ? Of course, the one that bit me in this case, at what request rate? Because the performance of an API or a system can be significantly nonlinear based on request rates. And then what variance and latency is acceptable? Is it okay if some things take 10 times longer, 100 times longer, 1,000 times longer? What would that mean for the customer experience? And similarly, if the system is built around throughput, the question is, well, with what parallelism, with what sizes of messages or requests, and again, with what variance is acceptable? Can it sometimes have, 10 megabits of performance and sometimes have 1? Does that matter or not? And so once you have that information, you have to decide where the right place to observe the performance of the system is. Most often people start with the service edge and they say, this is how my system works. Look, I've got it instrumented. Here's my 200s, 400s, 500s. The thing is that that's not actually the experience of your users most often. It's probably like this. So you think everything's fine, and they're having a different experience. It could be a better experience. It could be a worse experience. It could be that your error rate doesn't matter to your users because they automatically retry everything or whatever else. But you have to establish those perspectives, and ideally more than one perspective. So often you want to look at the client, probably the load balancer, and the service edge to understand how things differ between those three perspectives and what might be causing that. And once you've established this perspective, then you need to start building a mental model of how you think these things will behave. And you could be totally wrong, but if you don't have something to compare against the unexpected, then when things are too slow or too fast, you can end up in a situation where you assume that behavior is normal when in fact it doesn't. You have expectations that you haven't expressed and it doesn't conform with those expectations. So once you have that model, you have to start asking, what am I seeing? And the thing is, like, it's because we don't have direct access to a lot of the systems we're responsible for, in the sense of like, we're looking at the processors and the network cards directly. We're looking at things that these systems generate, telemetry that makes them hopefully observable. But unless you understand where that telemetry actually comes from and what it is and is not measuring, it's easy to start making assumptions that aren't correct or aren't going to be coherent with each other. So when you figured out what you are actually observing with enough confidence, then you can start asking, why am I seeing it? Are my observations confirming or disconfirming my mental model? What might be causing these changes that I haven't expected? Is it the networking slower? Is it a change in the hardware? Is it bad instance? But overall, and the thing I'd like to take you all to take away from this today is the lesson that variance happens along dimensions. When there's variance, it's not because there's magic, probably ever, but at least the vast majority of the time, it's because there's variance along a dimension that you haven't foreseen, that you haven't observed, that you haven't brought into your mental model or telemetry model. And so some of the things that I would generally recommend as things to observe variance along is region, availability zone, instance, or pod, or both if you have both, networking groups, security groups, and then other things like customer IDs. So are different customers experiencing different kinds of performance and why? And then also things that reflect change, like the version of the software or the version of the config. And if you aren't versioning your config, you should probably do that. The other things are what's at the other end of a connection or what's at the other end of a request, remote regions, remote availability zones, remote DNS, remote IPs. So the question is, do I have the dimensions to understand the behavior? Are they possible to get? How do I deal with the cases where I can't get the dimensions I need to understand the behavior? And if you start thinking about this, maybe a lot of the time you won't, but you realize you'll keep the uncertainty in your mental model about what dimensions you are and are not seeing. And that uncertainty will help you when you're troubleshooting. It will help you when you're architecting. It will help you when you're making tests to see when there's failure, how that failure affects your system. It's essential to keep that uncertainty in your mental model to be effective. And so, when understanding complex behavior means looking into abstractions that you normally ignore. So dig into that magic. Sometimes it will continue to be magic, and that's okay, but you'll be ready for the uncertainty it implies. One last thought that I'll leave you with. Imagine if you could look at the health of a critical cloud service API dependency across all your services the same way. Imagine if you could have the variance that matters, that is known to matter, built into the SDK you use. Imagine if you could compare the health of that API that you use against other people, instead of having to ask on Slack or Twitter if other people are experiencing similar issues. Imagine a real status page based on actual use along the dimensions that matter. So this is my current project that I'm working on, and I'm interested in more collaborators because we have an opportunity right now. We haven't talked about OpenTelemetry and OpenTracing much, but there's a new standard that's come out that's had widespread adoption called OpenTelemetry. And with this new standard, we have the opportunity to create the standard instrumentation and the tools that we all use, so we can look at it the same way and understand them the same way, and then also compare those results. So thank you. And I'd like to invite you to try the Lightstep sandbox at lightstep.com/play. I'll show you a little bit about that, but let me jump over into the live data really quickly and show you what this looks like right now. 1 second.
James, while you're doing that, I do want to remind the audience that we are taking questions at any time. So if you have a question for James, please go ahead and use your GoToWebinar control panel and submit your questions. We'll get to as many as we can when we get to the question and answer period.
So this is the interface for services. And right here we have, this is the main operation I use now, which is called ping. This is in the current generation that I'm working on for the real status page. And so if we have differences in performance, let's actually zoom out a little bit. So this is the last 4 hours. Let's zoom out to the last day. So we can see there's been some variance. Let's look at, let's compare this amount of time with this amount of time, just to show you how this works. So this is a feature that we have that collects these high dimensionality, with the dimensions that matter, that allows you to compare with all these dimensions arbitrary different pieces of time. So this is the operation graph that basically is the same as the representation that was in that that trace with the different pieces of spans, but this is all of them together. And this shows from this operation that goes to this, what amount of time takes the most time. So if you're having slow DNS or slow TLS or slow TCP implying a network issue, these yellow things will get bigger. So it looks like right now, actually, TLS is relatively slow, even slower than the response time, which is actually a little bit surprising. Looking at the comparisons here, there's not much difference there. Yeah, TLS is 3.2 milliseconds longer. DNS is slightly shorter. I don't think we have a strong explanation of what's going on here. We can also filter and group by, so things that are part of this. So we can filter by, actually I need all traces to show this, all spans. Reuse true, reuse false, and this will show us only the ones that didn't reuse. That doesn't show us anything. This is the fun of doing things live. In many cases, this will service out differences. This is the only difference between these two of 2 milliseconds, or for P99, 3 milliseconds to 6 milliseconds, which is probably too small to be interesting in the normal case. Let me zoom out further and see if there's anything else that has a bigger difference. So that's a bigger difference. Let's see what's going on there. And, oops. Let's make the regression on this side. And then baseline, compare. So this looks like there was a lot less reuse between these times, which is surprising and interesting because reuse is usually pretty stable. So I probably won't be able to figure this out right now, but that's quite interesting that we see variance based on reuse, and we can surface that out across thousands of traces pretty quickly. To give you a look at what these things look like overall in dashboards, let's look at the US East 1 dashboard. So this jaggedness that you can see here is the cache situation. So we'll zoom in, and mostly the responses are all cached, no matter where we're going. So this is US East 1 to Europe 2, Europe West 2, this is Asia East 2, and you can see the performance is essentially the same because it always is answering from the cache. But occasionally it doesn't, and you have these spikes up to where latency would normally be if it was actually going cross region. We go out to 30 days, you can see the change, most recent change, the caching was made across most regions in early January, and they turned it back on for pretty much everyone during that time. So interesting things you can see when you're looking. It's a good idea to keep an eye on these things and to keep track of the performance of your systems in a similar way. So there's, we talked about play. I can jump over that really quickly. And so what this is, this is the Lightstep sandbox. So what this does is, I've just been showing you with real data with a specific, relatively limited case, but this will walk you through the same sorts of scenarios. And there's several different scenarios, and we're adding more. But there's monitoring deployment, debugging error, and resolving a performance regression. And you can use Sandbox to experience what those processes are like in Lightstep. It's pretty neat. So that's it for the demo. Let me go back over to this. Sorry. Oh. There. Okay. So I am ready for any questions that we have.
All right, great. Yeah, if you have a question for James, go ahead and use your GoToWebinar control panel and submit your questions, and we will go ahead and dive right on into what we have so far. First question, let's see. What's one dimension that people routinely overlook when building out their telemetry?
I think it's surprisingly common to overlook version. Yeah. Because the version of the software that you're running tends to be the thing that varies the most. So if you aren't tracking all your metrics by version, there's lots of things that you can't do. And one of the things that I learned the hard way as well is like, you may think that you've deployed your software, and you may think that your software version is the one that's handling requests, and it turns out that there was some failure somewhere, or things just went a lot slower than you thought. And so the telemetry you're seeing isn't from the version of software you think is deployed. And that can lead you down some pretty significant rabbit holes. So I would have to go with version, and maybe like next to that, I talked about config version, but like the combination of a software version and config version can create significantly different behaviors that you can't assume that you know where a particular request went through, because a lot of these systems that we use nowadays are eventually consistent.
All right, great. Yeah, it's a good point, actually. I don't think a lot of people think about that. Okay, question here. Okay, this is actually more of a statement. You have convinced me to never use cloud functions or lambdas for anything for which I really care about performance, latency, consistency. Comments?
I mean, it's fair-ish. Like,
yeah.
The thing is that they are really easy to get going. So if you need to figure out whether the thing you're doing is worth doing, they let you not have to deal with a whole bunch of infrastructure that you may or may not need. If you're like, hey, I want to try this experiment, you can deploy that code in like 10, 15 minutes. And depending on what your alternatives are, it's usually a lot longer than that to use something that aren't functions. And they scale out very easily. Are they less consistent than the same code running on instances? Sometimes it's less obvious where they're inconsistent. So I think that that's a fair criticism, like, because you can't tag by instance ID, for instance, or pod. But at the same time, I think that there is a surprising amount of inconsistency that often goes unobserved within the same availability zone, or even on the same instance between different pods.
All right, great. So next question here, and please, if you have a question for James, go ahead and use your GoToWebinar control panel. How can people who aren't network specialists learn what they need to know to operate their systems? So
it's my favorite answer to this is that, and I'm a learn by doing kind of person. I learned to program by reading the source code to traceroute, which is like sort of crazy. So like which is a tool that you can use to see network performance by sending packets across the internet. I feel like the best way to get an intuitive feel for how your system behaves, enough for you to care about doing the rest of the observation or instrumentation or learning, is to cause failures on purpose using chaos engineering approaches. So if you if you use some of the different chaos tools to like start dropping packets and then see how your application behaves, or start making things slower, then you start getting the feel for like, yes, the network does actually matter. Like, it isn't that I call this API and it just appears somewhere else, or the results appear back to me. Like, these things can and do change, and they will change when I'm not controlling them. But if I do control them in a chaos experiment, then I can see the impact of the actions they have taken purposefully to make the network visible. And so I feel like, at least for people like me, that helps motivate the learning. And then you can start digging into like the ladder diagrams for networks and whatever else, and know why it matters to the problem you're trying to solve.
That's a good point. Okay. All right, great. Next question. I'm new to serverless platforms. In general, does this serverless architecture with cloud functions perform as expected in terms of characteristics like latencies, throughput, and resource utilization?
I mean, it depends on what your expectations are. I was, on the whole, pretty pleased with Cloud Functions, in that, like, for the stuff I was doing, I was able to have a relatively small pool and be able to run my experiments on. When I was doing it all on Cloud Functions, it was less than $5 a day to run the experiment, whereas like spinning up instances and keeping them up and running Kubernetes or whatever else on top of them would have been significantly more. And so like it's definitely good for when you don't know how much you scale or have to scale. I think the tricky things are these different sorts of resource limitations around, particularly around CPU throttling, that isn't something that you're used to thinking about. You're used to thinking about maybe running out of CPU, but you aren't used to CPU suddenly becoming, 1,000 times slower, maybe, when you've run out of your capacity, and that's a little tricky. So like doing CPU intensive stuff inside of Cloud Functions is probably still not a great idea, but for doing data transformation on the fly, I think it's a great solution.
Excellent. Okay. Okay, guys, we have plenty of time for questions. So if you have one for James, go ahead and use your GoToWebinar control panel. Our next one here is, well, first of all, thanks James for the informative talk. And then has Lightstep been actively used by financial services institutions as well? Would love to listen in on data privacy in a financial services business context.
I don't think that there's any public information about that. So I don't think I can comment. Data privacy, though, generally I can talk about. It's tricky, especially with GDPR and the new also regulations in California, because if you put regulated data into your telemetry system, we provide tools to make sure that doesn't get to us, and if it does get to us, to remove it. But it's still tricky, because not everybody at every point in the system has visibility into that, or understands that the data that might end up a field could end up being sensitive. And so that's why we provide the tooling in both senses, as well as retention policies to try and limit that. But yeah, it's actually a really good question, because telemetry systems of all different sorts, observability platforms, end up becoming a place where PII or regulated data can end up. And that's something to just keep in mind and make sure that you have a strategy for, and your providers have a strategy for.
All right, great. Let's see. Well, it looks like that is all the questions that we have right now, but there's still time, guys. If you want to go ahead and submit one, please, just like I said before, use your GoToWebinar control panel and submit the questions. While we're waiting to see if we do get any more, oh, we just got another one in, so never mind. We'll go ahead and ask that one. Do these OpenTelemetry or OpenMetrics allow me to not perform any vendor lock-in?
Yeah, that's the whole point. So that ideally you shouldn't have to do any instrumentation, but we're not in that ideal world yet. But if you do it, have to write your own instrumentation for a particular problem or a particular part of a problem, that the data that's generated from that telemetry can be sent to any or all vendors. If you wanted to do a head-to-head comparison of all the vendors that support OpenTelemetry, you can do that, because part of it's standardizing the way that context is propagated. It's standardizing the way that systems are instrumented. It's also meant to standardize the way that frameworks and even at the language level things are instrumented, so that when you get your Ruby on Rails or your Java Spring Boot or whatever else, it automatically generates telemetry in OpenTelemetry that you can use with whatever vendor you want.
All right, great. Got some more questions in here. How are the APIs today? Are they stable or not?
This automatic caching thing threw me for a loop as I try and write follow-up reports to this. They have been pretty stable. There are a few issues over the summer, but things have been pretty stable in the fall and winter. Except for like this, it's suddenly 200 times faster and suddenly not. And now it appears to consistently be at that faster rate. I actually tried to open a support ticket and they're like, wait, you're complaining that it's too fast? I'm like, no, I'm not complaining. I just need to understand why it's faster. So like in general, like there have been very little from my arbitrarily generated ideas about service level objectives for this. They've been pretty stable for the last couple months. That has not always been the case. There were a lot of troubles earlier in mid last year.
Okay, all right, great. Another question here. How do people most frequently start with distributed tracing?
That's a very general question. I mean, I think it depends on what role you play and who you are and what you're trying to observe. So if you're someone who owns a service that other people depend on, usually the easiest way to get started is to look for one of the tool sets that does auto instrumentation for the frameworks you're using. And when you have that, then you automatically get traces for the different components that are part of your system, including requests into your system, requests to databases, depending on the framework, different sorts of common operations like your object relational model setups, and also your requests to other systems. If you're on a more platform or ops team and you don't necessarily own a particular system or you're responsible for systems that you can't easily change, then it's usually easier to start instrumentation at the edge, either with load balancers or with a service mesh if you're using something like that, and start observing the behavior of the system from the outside. And it's still possible to extract information dimensionality from that so that you can see how particular services handle particular requests. And yeah, I mean, if you're a framework writer, then you should write it into framework. But I think we're still getting there with that.